Yeah, you can use the book. Yeah, you can use the book. And that's why you need the book. Okay, you guys here? Hello? Okay. So let's get the class started. I think a lot of you did pretty well in the last quiz, which is good. Average was near 70, which is pretty good. As a lot of you got 100%, but we do have a few people who either didn't do the quiz for some reason or who didn't, with really low score. So you might have to work harder in the next few weeks, even though we dropped some quizzes. Well, we dropped 2 so far, but still, making effort to make sure that you get your best so that you really not say, okay, that one's going to be dropped. I don't care. That's not going to work for you because you never know which one you're going to do better, which one you're going to do worse. So just try every single one, you do the best, and then eventually you'll really get all the benefits out of that to drop the quiz. So today we're going to continue from where we left from last week on chapter 7. And this we're going to flip all the way over to where we stopped. We talked a lot last week. Oops, hold on. We should, example, digitizing, yeah, we already got here. We passed this point, yeah. Different by pause. Okay, we're almost there. So we stopped here at how to bias BJT, and we said, well, the R1, R2, it forms kind of, and VCC forms a Thevenin's equivalent circuit, and we can derive the voltage, Thevenin's voltage, and Thevenin's equivalent resistance, and we'll put it back. The reason we have to do that because there is a current flowing into the base, not like a MOSFET, there's no current into the gate, so it's easier. However, you will see that in the future, now this is a very easy way to do the calculation, but in some cases, we also try to neglect IB for some calculations. And one of the confusion I got asked often is that, how do I know I should avoid like neglecting IB or not neglecting IB, or it depends on the situation. And then you see the problem in the test, for example, the problem would tell you to calculate IB, and then you definitely cannot neglect it. Or you need IB to get IC, you definitely cannot neglect it. But if the focus is on getting the gain or something else, you might say, okay, you can neglect IB, or you can assume beta is infinity when you calculate the gain, because in that case, that IB doesn't really impact too much about the output. So this is, it's important to go from there to here. And then, but most importantly is that once we get to do the amplifier, you're going to see a lot of circuits in the future have capacitors in it. And last week, we already discussed what happens to the capacitor at DC and what happens to the capacitor at AC. Now remember, capacitor is an AC component. So therefore, for DC, it's an open circuit. So when we do the DC biasing of this one, we will simply disconnect input, and we also short this source to ground, and we also disconnect the output because there's capacitors to do that. So therefore, what you're really doing is you are actually so we can derive the DC circuit by simply try to eliminate this and eliminate this and eliminate this. So it becomes a very simple circuit which we already discussed last week on how to calculate the DC biasing. So for DC biasing, now you got this circuit, you get a DC voltage here. There's no current in the source. Therefore, this two becomes a voltage divider. You can easily find the voltage at the gate. And from that, you have VGS. Now, knowing VTO, you can find the gain GM. The transconductance GM is equal to 1/2, not 1/2 here, but KW over L times VGS minus VT. So that's how you get your gain. You're done with your DC biasing calculations. Now, if you're given VA, you can also calculate RO. So those are the equations again. Try to either memorize or write down somewhere easy for you to access. Once you get the DC circuit and analysis finished, now you can go ahead to derive the small signal equivalent circuit. So we did the DC. So now, so this is the DC bias circuit again, just to illustrate like how this is drawn from last slide. And from here we can calculate GM, we can calculate RO, and so on. So basically, those two apparently is calculated from VGS, and VGS calculated by doing the voltage divider is okay. So and now you can find the equation to calculate these numbers. So from here, we can further derive the small signal circuit. Now for small signal, this capacitors become short circuit. So therefore, it is good that if we redraw the circuit, let me before we go to a small signal, let's redraw the circuit so that it helps us to redraw the small signal equivalent circuit, which means oh, actually, I'm sorry. On the previous slide, I need to go backwards. I made a mistake here. Because for the DC here, actually, we for the circuit here, we cannot neglect this one. We neglect this one, not the RS. So therefore, there will be a RS over here for DC biasing. So just try to maybe make it better. Okay, so that's your VGS. Okay, now we go back to here. So now we go back to here. So this one actually now is going to be a short circuit because for the oops, because this remember this is C here. So the C here really makes a short circuit. So this capacitor makes the AC a short circuit, and this is being shorted. So therefore, the source is directly connected to ground. And then at the output, this CC2 becomes a short circuit as well. So therefore, we have this RL, and then you get your V output over here. So this, once we get GM and RO from our previous slide, we can now draw the small signal equivalent circuit. Now this circuit, because there's nothing at the source, so therefore it's easy to use a pi model. Remember, pi model actually connect this to ground is much easier. So therefore we can use the pi model. So we can do this all together to redraw it, and then I'll give you the correct circuit afterwards. So the steps to draw the small signal equivalent circuit model is to start with the pi model in this case, or some cases use T model later on. We're going to talk about that. Once you do the pi model, you have all the three terminals, the gate, the source, and the drain. And then you find which one is connected to which terminal, and then connect all the components, and you complete the circuit. So in this case, the pi model will look like Okay, so we have the pi model, very simple model. Input VGS, GM times VGS is the current flowing through gate down to source. Now we need to look back at the circuit. You can look at this one, in the long run, you know what it is, but for the time being, let's look at this one because this one already removed the capacitors and have all the components. Now, let's start from the gate. What are connected to the gate? You have this one connect to ground, and this one connect to the DC, but DC is a short circuit for AC signal. So therefore, you have two resistors connect to ground, and then you have another resistance connect through to the input. So therefore, we have three components at the gate. So one is RG1 connect to ground. The other is RG2 connect to ground, and then another one is what do they call it? Our signal and connect to input of V signal. Right. So now we finish the gate side. The next, let's look at the source. What is connected to the source? Ground. So we'll simply connect the source to ground, easy. And then what is connect to the output or the drain? Here, RD1, RD connect to ground. Now this, remember, the DC is over the ground, and through RL to ground. So we have two resistors. So RD connect to ground, and then RL connect to ground. And sometimes, if VA is given, we need to connect another resistance, which is from drain to source. From drain to source is RO, is the early resistance. Okay, so from drain to source and source to ground. So basically, you can connect this one. Now, often is, often we write that one inside to make it easier. So you guys, I'll do the same thing. Just so this is GM. So this is RO connect to ground. Right? So we have three resistors at the output. So to analyze the circuit like this, it really becomes very easy. First of all, we want to look at the input. So the input is VGS is a voltage divider of input, right? So this two parallel with this one. So this VGS equal to V6 times the total and divided by this. So that's input is your voltage divider. And your output, your current is given, GM times VGS. And this three all in parallel. So your output is very easy. So therefore, for me, actually, I should be able to write the output right away as VO equal to RG1 in parallel with RG2 divided by RG1 in parallel with RG2 plus R6. That's my input. And then times V6, get VGS. And then I multiply by this three resistance in parallel. RO in parallel with RD in parallel with RL. Okay, and then I add a minus sign. So this three in parallel times the current, and then times GM. So we forgot about GM. So we have to times GM. So where's this one? So we have minus times GM. Minus equal to VO. So I got the answer right away. But if you feel this is more difficult, you can certainly go step by step. First, find a VGS, and then find GM times VGS, and then find VO in the last step. And then given this, don't remember this minus sign in this case. So this equivalent circuit basically already given. So that's how we do it. This actually previously was an example to actually do the stuff, so if we want to do a BJT, you see the circuit is almost identical, except for MOSFET is replaced by BJT. So simply You can do the same DC biasing by eliminating the capacitors. I mean, have them open. You get the DC biasing circuit, and then we plot the small signal circuit after that, right? So let's look at how we are going to. So the DC biasing circuit, we open this one, we open this one, we open this one. So we got this one. We got it. So we have now equivalent circuit. So in this case, if I'm not asking you to actually calculate how much VP is going to be, you can, it wouldn't be too much wrong if you do just neglect the base current and do the voltage divider. It should be fine because that's going to only cost you about 1% error in the final calculation. So it wouldn't be a big issue. But if I'm asking you to do the Thevenin's analysis before you actually do the DC analysis, you should do that. So given the question, you should do that. So based on this DC analysis, now you can do the small signal. So for the small signal circuit, basically you're going to do the same thing. You do the pi model in this case, because in the small signal, the base, not the base, the emitter is grounded. The emitter is grounded through the capacitors. So therefore, for AC signal circuit, it's going to look like this. It's important is to know this one here. It's important to note that the base is actually grounded through the capacitor. So that will make your life a lot easier, that you can use the pi model. So from here, we can basically draw the pi model, because that one, you replace this one with the pi model, and you connect all these three to the base, you connect these two to the collector, and then you ground the emitter, and also you can add RO, the early resistance, at the output. You get almost the same equivalent circuit as what we get for the MOSFET, except there's RPi. Except, remember, there's RPi. Now, with this RPi, what have changed with the previous calculation? Now, since this is ground, so basically you are separating the input side and the output side, so there's no problem. So the only difference of the previous MOSFET calculation was nothing here. So therefore, the input is divided between this one and this two. But in BJT, you have three in parallel instead of two. So the only difference is we are going to all three in parallel to get the voltage divider here, to get VBE, and then we got VBE here, we multiply by GM, and then we use this current multiplied by all these three in parallel, we get the output. So we can basically find the output now to have VO calculated as, again, minus sign, don't forget, and then don't forget a VGM. And then on top here is we're going to have RB1 in parallel with RB2 in parallel with RPi, and then divided by same RB1 parallel with RB2 parallel with RPi plus R signal. So that's the input side, and the output side is RC in parallel with RL in parallel with RO. So in one step, I basically can write the voltage. Now, if we want to calculate the gain of the circuit, the gain usually is expressed as voltage gain, like AV. A means the amplification. So the gain, the voltage gain is called AV. The GM is sometimes called gain, but sometimes called transconductance. It's actually intrinsic gain, sometimes called. But voltage gain is the actual gain of the circuit, which looks at how much input and how much output. Now, you would simply use VO divided by V signal, and you will get the gain, which is going to be everything else here except you move out, we are as signal on this side, so you get the gain. Now, if we plug in all the numbers, you'll find out that, well, this is a kilo ohms, and this is actually a voltage divider less than 1, maybe 0.5, maybe 0.2, depending on this guy. If this guy is big, the voltage divide, this is small, but if we signal is small and then this is big, if input resistance 0 here, and you actually get this, everything is applied to the input side. And GM is usually in the 20s, 30 or single digits. So you multiply all this together, you find that this gain is actually quite large. Sometimes it can go as high as 50, 40, or 100, depending on the parameters that you put in. So this is our common emitter amplifier. Again, use pi model, so we're going to skip that. We did that already. When we have a common emitter amplifier, sometimes you will see a crazy configuration like this. What this is? Well, this means that they say, okay, there is actually a resistance that is bypassed for AC, but for AC, this is a short circuit, but this is not. This is RE. For some reason, they designed this circuit, or maybe they just put this to confuse our students. But in any case, if this resistance is not shorted, the pi model will become crazy. If I draw the pi model here, you will see how this becomes complicated. So this is going to become, let's draw the pi model here. And this is our pi model. This is our O, our C, L. This is your output. You see, this is where the problem comes from. Because if you have RE at the emitter, these three are no longer in parallel. These two are still in parallel, but not R pi, because R pi is connected to RE to ground. But you cannot simply add these two because there's current flowing here. So these two are also not in series. Do I make it clear? This is very important for you guys to move on our next few slides. Yeah.
So if you look at the emitter and it's not just to ground, you use T model instead.
Well, that's our next what we come up to, because first of all, we need to understand, like this R pi is not in parallel with the input resistance. I mean, the gated resistance here. It's not in series RE. So if you want to solve this with a pi model, you have to do nodal analysis over here, and then it becomes very complex when you write it. You can still solve it. I mean, it's not impossible. It just becomes more difficult. So what do you do then? That's where pi model comes really handy, because for the pi model, you still use the here. This is the T model here, and we actually use this pi model. For the pi model, you have resistance here. RE. Now this RE is not that RE. Okay, so this RE is an external resistance. This little case RE is an internal resistance that we calculated for the pi model. Okay, so this RE is R pi divided by beta. Remember that, or beta plus 1. And then, so this is a small, very small resistance, usually in the hundreds of ohms. But this RE can be in the kilo ohms. So actually that makes your life easier, because sometimes you can even neglect this one. But in any case, once you have the pi model, you see what's interesting is that your RB1, RB2, and RE, or the total of this one, are they in parallel? No? Why not? I see yes, I see no's. Is this one is, are these three resistance in parallel? Yes, because they're connected on the top at the same point. At the bottom, they are grounded. See, yeah, they have the top and the bottom, but they are all in the same terminal. Yes, they are in parallel. But why this case is not in parallel? because the bottom of this one is not ground. The bottom of this one has another thing connected. So this is not in series because this current here. This is not in parallel because this bottom is not ground, but this two are ground. So they're not connected to the same thing. So therefore, it's critical to understand that this one, and this one, they are all in parallel. Once they're in parallel, you can simply merge all this one into one resistance. So that one, basically, we can draw the circuit over here and say, well, we're going to draw the equivalent circuit like this. Let's call it R in prime. Okay, and then they're all in parallel, but here you also have this resistance coming, current coming here. So now you can calculate, you can use a voltage divider between these two, or can you? Can we use voltage divider? Yeah or no? Well, actually, no. The reason is you have current flowing here, so you cannot use voltage divider. So, but see, the idea is that you have the current flow here, but you know the current here is alpha times IE, and IE is the current over here, right? So, and then the current over here is IB. So basically, you really have to look at, do a little bit of nodal analysis to find the current flowing this way, and current this way. But so by doing that, you will be able to find how much current flowing, IE. Use beta times IE, you get the current over here, and use this current multiplied by this resistance, you get the output. So it will be easier than the pi model, but still you don't simply use a voltage divider over here. So you do a nodal analysis over here. So the nodal analysis would say this current coming in, let's go to I1, and this current coming in, this is I2, and you have current, this is I beta times IE, so this is IE coming in. So ideally, you have IE here, this I beta times IE over here. So this will be, oh, sorry, alpha times IE, not beta. Alpha times IE, but this IE over here. Now, remember in the current, in the circuit, instead of doing nodal analysis, of course, there's another trick, is that IE equal to beta plus 1. I mean, let me do this in a whole, actually easier way for you to understand. So IE equal to IC plus IB, and IC equal to beta times IB plus IB. So therefore, this whole thing is equal to 1 plus beta times IB, right? So which means if I do the IE, and so this IB and this IE, the IE equal to 1 plus beta times IB. So therefore, you already know how much current flowing here, and you use that IB. You use alpha times IE. Alpha is beta over 1 plus beta, right? So and then you can eventually find out how much is here. So the nodal analysis here becomes really easy. Is IB equal to, basically it's IB plus IC equal to IE, and okay, so we have right. And then we okay, so if I wanted to further do the voltage over here, so I can have this voltage equal to VE equal to IE times RE plus RE, right? And then we will have IB
Hold on. That's not true. One second. This is my notes. Make how to make it easier to calculate. Okay, yeah. So we can find VE equal to, which is V sig divided by R sig plus this R in prime. This R in prime is equivalent to RB1 plus parallel is RB2 and in parallel with RE. So that's our VE. And from here, so we can calculate IE. So we find VE here, and then we plug in this VE here, we can calculate IE. Once we find IE, we can use this one to calculate the current, and then plug in that current, we'll finally get the voltage. I don't have a place to write it, maybe next slide. Yeah, no, next slide. So then we can have, well, alpha times IE multiplied by the parallel of this resistance to get the output. Okay, so this means we avoid the a complex nodal analysis where you have to manipulate, but in this case, we simply derive the one step by step. We don't have to like do those complicated circuit analysis. And if we have, remember last time we talked about there are three types amplifier for each MOSFET and BJT. So for the MOSFET, remember we have common source, we have common gate, and we have a common drain. And for the BJT, we have common emitter, which is the most popular one. And then we have a common drain, which is the emitter follower. We're going to talk about it later. And we also have a common base amplifier. So in this case, if you have a common base, for DC, basically you can forget about this one and forget about the output. So you can see there's a negative voltage, this is ground. So therefore this is bias is down. Now for AC, the input is connected to the emitter, and there's another resistor emitter. So therefore, naturally, if there's something at the emitter, use T model. That's the general rule of thumb. If nothing at the emitter, use pi model. If emitter is grounded, use pi model. But if something at the emitter, use a T model. And then you can look at the collector. You have two resistors for AC. So use a T model will make your life much easier. Let's see if we have actually a T model given already. Yeah. So the T model, again, you see the blue portion is actually the T model. And once you got the T model, you see the base, the base is grounded. So therefore, it's called a common base amplifier. So we ground this one. And then this is internal resistance RE, and this alpha times IE. And then at the input side, you have V signal connect to the signal input, and then through RE to ground. So, and then at the output, you have RC and RL. Right? So now the most important stuff is to calculate what is IE and use alpha times IE to get the current, and use this current times this two in parallel, or sometimes you also have RO, and then to get the output voltage. To do the analysis of this one, in fact, we what we do is we first of all find the input resistance at this point. The reason to find resistance at this point is to look at the important thing is to look at this is ground. So this point is ground. So therefore, we can redraw the circuit. We basically, because this is ground, so that's very important for this common base analysis. We can redraw a circuit to connect this to ground. So therefore, the circuit will become something like this. I tried to explain here. So RE is naturally grounded. And I draw the small RE to ground because you see from here, basically, which is the point over here. This point is this point here. And from RE, it goes to ground. So therefore, this RE is naturally to ground. So that's why it's important to do that. So this is your E to ground. And then basically you have this like here. This is why this is a good way to look at the RC and RL, this will. And this is alpha times IE. So because this is ground, so therefore all current flows to ground. So therefore I just have the current flowing to ground. So this again, this is ground. Let me mark this as ground. You see how simple this circuit becomes? Basically, you have RE and big RE and little RE that are in parallel, and then in series SIG. So therefore, by doing voltage divider, you can find the voltage over here. Once you find the voltage here, you can find the current over here. Once you find the current, you have current over here. By multiplying the current with these two resistance, you get the output. So that's why if you look at the steps for the calculation is we find R in. So this R in basically is equal to RE in parallel with RE. And then you have resistance, you have a voltage here. Let's call this VE. So you have V equal to voltage divider between voltage of R in divided by R in plus, you get this VE. Now, once you get this VE, you can calculate IE equal to VE over RE. And then once you have IE, of course, you can know alpha times IE. And then eventually you have voltage output equal to minus alpha times IE times this RC in parallel with RL. So therefore, this will become to minus V6 times this voltage divider, which is R in plus RSG, and then multiply RC in parallel with RL. So you can easily find the whole gain. And now if you divide this one on both sides, you get the voltage gain, which AV equal to minus R in over R in plus RSIG times RC in parallel with RL. So sometimes if you want to include this RO, you can do that as well. That becomes if VA is given, you can do this. If VA is not given, just forget about the RO, and you get the whole circuit result. So that's the common base. And once you know the common base, now it's easier to understand the common collector, or sometimes called emitter follower. The reason is that you have something, again, at the emitter. When you have something at the emitter, use T model for the small signal. Now, before you use, usually when we do, again, amplifier analysis, that we need to, like, first step is to do DC biasing calculation. So for DC biasing calculation, you get this one, removed, and you got this input removed. So it's very easy to look at the DC biasing. Okay. Now, after doing the DC biasing, you find RPi, you find GN, and we can move on to the small signal. Again, we do the pi model, T model. Let's do the T model. Here, I just want to illustrate how difficult if we want to use a pi model. Again, nothing wrong. Okay. So you're just saying that the circuit becomes more difficult with the pi model. So let's do the B, the E, and a collector. That's the pi model. So now we identify which ones connect to the base. There are two resistors, this one and this one. Of course, this becomes a short circuit. So we have one connect to ground, and then we have one I'm sorry, just my writing is not that good. Okay, so and then the problem, of course, is the RE to ground, and then we have this. Oops, actually, it's another mistake here. The collector is actually grounded. And the output is over here. You see the problem again. This R pi and RB, they're not in parallel, and because you got something here. So if you want to resolve the circuit, you need to do nodal analysis over here, and you have to do another nodal analysis over here. So basically, you have to do two nodal analysis, and then you can find out what the output voltage. The output voltage is actually the current over here is the voltage drop over here. So therefore, it's more difficult. So therefore, we don't do it, and therefore we use T model. So with T model, yeah, let me draw it here before we show the actual circuit to make it life easier. Because for the T model, you have so this is our T model. So for the T model now, we need to identify again what is connect to base, what is connect to emitter, and what is connect to collector. So look at this circuit. What is connect to base? We have RB connect to ground, from base to ground. And then we have also C is short circuit, so now we have RC connect to the input source. So therefore, we would connect the base two things here. Here doesn't work there. So we have this one, RB connect to ground, and then we have input R. Oh. Okay, sorry about that. And then we have input. Okay, that's the base. And what is connected to the emitter? There's a capital RE to ground, right? So there's capital RE to ground, and the output, of course, it's over here. And what is connected to the collector? Ground. Okay, so now you have a circuit which has this is the ground, is alpha times IE, and this RE, RB, so and your output is here. So doing the circuit analysis on this one is much easier once you identify, forget about this because there's nothing connected here. Even if there's something connected here, you can connect this in parallel to becomes one resistance. Okay?
What happened to RL?
What happened to RL?
Yeah, why isn't it part of the team?
Good observation. What do you think we should put RL?
Is it the emitter?
Yeah, with the emitter, and it goes to ground. Right, so that's why I forget about that one. So RL, it goes to ground. So we got this RL, but this RL and RE are in parallel. So eventually they becomes like a one equivalent resistance, and then that is in series RE. So you can further simplify the circuit to something like but of course, in this case, we don't have the voltage. The voltage is somewhere in the middle. But this is this resistance here. Let me call it Rx. So this Rx will be RE plus RE in parallel with RL. So in this circuit, you see these two are connected at the same terminal and the same ground. Therefore, these two are actually in parallel. Okay. So once you get this in parallel, and then you have voltage here, now it's easier to calculate the voltage over here. But remember, this is not a voltage divider. The reason is you have a current flowing here. Okay, so the most mistake that our students make is, oh, this two in parallel, okay, easy. And this, oh, maybe in series and not a voltage divider. You're totally wrong because it's not a voltage divider because there's current flowing here. Actually, the voltage drop on here is much larger than the voltage over here. That's one thing to be very careful. It's another voltage divider. Right? So let me see. So we got this calculated, but in this actual circuit, you also put a RO. So if VA is not given, forget about this. But if RO VA is given, you put this here. It makes the circuit actually a little bit more difficult to do. So probably for you guys, forget about this one for now. So make your life easier. So sometimes it might make sense to do say so again for this type if the circuit is further really simplified and we can derive the gain by the simplification of this one is forget about the capacitance, forget about the DC biasing, forget about the internal resistance of the voltage source. So therefore, this one will be fairly easy to derive either from pi model or sigma. We can start from pi model to see if we're going to make it work. And then we can look at the T model to see how simple that can get into. So for pi model, so this is your pi model. With the pi model, basically, we need to, again, the reason I'm trying to again, is just want to remind you that these two resistors are not in series. So it is not a voltage divider. In order to solve for output, we have to do the nodal analysis over here. So we have to do the nodal analysis here. So in order to do nodal analysis, we can assume the voltage here, we call it VE. And we can write a nodal equation for the current flowing this way, current this way, and current this way. So basically, we will have V in minus VE divided by R pi is the current flowing into the base, plus current is GM times VBE, and then and this will actually will give you the current equal to VE over RE. So we have we basically look at nodal analysis. We have current flowing here, current flowing here equals to current flowing down, RE. So now you get the nodal equations, but the nodal equation has input is given, GM is calculated, VE is not given, and VB is also not given. So basically, we have two variables we cannot solve. So in order to eliminate one variable, we can find that what is the VB? VB is actually V in minus VE. So VB is V in minus VE. So we're plugging this one into this equation. Right away, you eliminate VBE, and you can resolve for relation between VE and VE. And VE actually is our output. In this case, VE is equal to with 0. So we can easily find this, not a problem. Okay. So if we want to, sometimes it's also important to calculate the input and output resistance. Now, the reason that we need to output input resistance is this. Suppose you have amplifier, then you have input, then you have output. And you get a gain of voltage. So if we have an input and output is amplified by in ideal case, you will have VO equal to AV times V in. But in fact, this amplifier, like when we build them using digital BJT or MOSFET, they're actually not ideal. Not ideal means this thing comes in with like input resistance or output resistance. So the actual equivalent circuit will be looking like this. Will look like so if this is like a voltage source, we can now so far you guys can actually have already have, oops, it doesn't work that way. Well, let me redraw this. Okay, so why is this input and output resistance like important? The reason is it's going to change the whole thing. Now, for example, if we don't have it, in this case, actually, you have this one here. So this is ideal case. So if you guys have an ideal input and output, like input multiplied by GM or whatever, the AV, it gives you VO. So that's what you get. So this is AV times V in. Okay, so that's your ideal case. But if it's a non-ideal, what happens is that, let me draw again this circuit over here. If you don't have, if it's ideal case, so this case, you have VO equal to AV times V in. So it doesn't change. So when you connect the input voltage and load resistance, the voltage here didn't change. Ideal case, nothing connected, load connected, and input connect, nothing changes, so output. But if it's non-ideal, you see what happened in this case? You're gonna have trouble because if our input, actually, this input might have, in the book, it's already called IC. Right. So in this case, we have this. So now you can tell me, is the output going to change or is it going to be the same as this one? It's going to change. And the reason is the input, these two become voltage divider, and this two becomes also the voltage divider. So we can easily write this input without just doing the detailed calculation. We'll know that this is going to be R in over R sig plus R in. That's voltage divider. And times the second voltage divider is RL over RO plus RL, and then this times. And you can see here, the voltage, the output is no longer same as V6. It's actually 2 voltage dividers. So, to maximize the actual output for the same input. So what are the things, what do you think ideally you would do with regard to input and output resistance for this one? Make it infinite with open circuit. Okay, if you cannot make infinite, make this as big as possible. Okay, if this is very big, this small, yes, most input goes to the amplifier. And for the output side, what do you do with RO? We make it as small as possible because the voltage drop on here is small. Ideally, we make this 0, but of course, we never make it 0, so we make it as small as possible. How small? Like if you make this, say, 1 ohm, if your output is 10 kilo ohm, you see how much the difference it's going to make? 0.1%, which we don't care. But if your output resistance is 5K and your load is 10K, you see what happens? Your output is only 2/3 of the overall amplification. So that's not good. So that's why it's very important that we design the circuit to have a very big input resistance and very small output resistance. And that is exactly what this the emitter follower is going to give you. Do we have space? Yeah. Well, we can do an example on a source follower, which is almost the same. For the source follower, emitter follower, source follower, it's almost same. You just simply have this T model. The difference, of course, this connection, and this one has no connection. So at the gate. So let's do the source follower. We do the T model. So here, basically, we have our input resistance, and then we have our T model, and we got RS here. Let me see if we got this actually correct. Just want to make sure. Okay, this is the MOSFET, so therefore it's not really connected. So the in here, and this is GM times VGS. So basically, what we need to find out is between voltage. So we in. What we need to do is this is the VO, okay? So this is V in over here, and then this is our. We need to find between VG and this VS. So we need to find VG and VS. We need to find the voltage between here. So VGS is not the same as V in. So this is a gate. This is source. This is drain. So basically, we need to find so our VO equal to GM VGS times S. So this is VO, and this is the current. GM times VGS, current going down, multiplied by RS, we got VO. So we can calculate VO, but of course, before calculating VO, we need to calculate GM for the DC biasing. Also, we need to know what is VGS. But VGS in this case is not V in, so we have to look at what is VGS. So basically, V in is connected over. Well, basically, it's connected over at the gate. So this is V in. So we need to find out what is the voltage over here, which is VGS. So VGS basically equal to V in multiplied by RS over RS plus RS, right? And so VO over plugging in those two that equation over here, we'll find VO equal to Gm times RS times okay, so AV equal to VO divided by V in equal to, hold on, give me 1 second. R in is equal to, oh yeah. Yes, somewhere I'm missing something here. VGS is yeah, this is totally wrong. Just about that. So let me come back here. So V in this case is I just apologize for previous mistake. So V in is from here to here, which is from here to here. As you can see, it's going to be VGM times VGS, the voltage here plus voltage here. So I can write V in as GM times VGS times RS plus RS. So that's V in, and then this is VO. So now I can write AV equal to VO over V in. So this is GM times VGS times RS divided by GM times VGS times RS plus RS. Actually, I didn't have to solve for GM times VGS because these two are going to cancel. So therefore, I got AV equal to basically RS over RS plus lowercase rs. But RS is typically in the 10 kilo ohm, and IS is typically in the 10 ohm. So just give you, this is in the kilo ohm range, and this is in the ohm range. So you have kilo ohm divided by kilo ohm plus ohms. Basically, this can be almost neglected, and therefore this equal to 1. So this is equal to 1. So RS is much less than S. So this is how we can find out the gain. Because output, the gain is almost 1, which means the output is almost the same as input, right? Because gain is 1, so output same as input, which means the output over here is almost the same output here. The reason because the voltage drop over here is very small. So for that reason, we call this a source follower, which means the source is following the gate. Basically, whatever you apply the gate, you get almost the same output, sometimes 0.998 or 997. So it's very the same as the input. So this is why it's called a source follower. If it's BJT, this is called emitter follower. And the calculation almost the same, gain is almost the same. Now, one of the questions we always wonder when we start to learn this thing, okay, if the gain is 1, why would you do that? That goes back to the previous slide I analyzed, because if we use regular amplifier, you're going to have a trouble because your input has limited, your output is limited. Therefore, your gain is much smaller. But with emitter follower, this input resistance tend to be infinity, and this output resistance to be almost zero. And why is that? Well, I think we're going to skip that one, but we're going to stay here for a little bit. If you look at the equivalent circuit, because there's nothing connected here, so therefore the input resistance is actually infinity for the MOSFET. If with the BJT, it is connected, but still the input resistance is very big. It's also almost infinity. And the output resistance is very small. I'm not sure if we got enough time to cover this. Let me do this. I'll probably look using one of the T model, like for the BJT, to find out the input and output resistance. If you look at the circuit over here, when we look for input resistance and output resistance, the way that we do this is to, for example, when we look for input resistance, we would short the output. You know, for the if you remember when we go to Thevenin's equivalent circuit for any like black boxes. So how do you look for input resistance, output resistance, Thevenin's voltage, things like that? So when we look for input resistance, we would short the output, and then we look for what is all the resistance. We do parallel series connections, we get the resistance. When we look for the output resistance, we short the input, and then we look for what's inside, and then look for the total resistance. If it's a regular circuit, it's very easy to do, but for the amplifier, the problem is that there's a control source. So we cannot simply do parallel series connection. We have to do something to do some derivations to make sure the current source is considered in your circuit. So therefore, let's go back to this equivalent circuit over here. So now, if we want to look for the input resistance, what we need to do is we need to short the output. Basically, if we short this one, and the whole thing gets shorted, so therefore this becomes the short circuit. And we apply voltage as input, and we find out the current. So we use input voltage divided by current, we get the total input resistance. Now, because this is grounded, so therefore you see this is in parallel now with this one, okay? And then these two are in parallel now. You get this resistance here, but this is not in series with this two because there's current coming in here. So we would have again do a nodal analysis, to find out what is actually the current. We can forget about this one, so that will make it easier. But of course, you can always include it, and the expression will become a lot bigger. So that's how we calculate the input resistance. Now, to calculate the output resistance, what we do is we're gonna like short this input. So if we short this input, this two becomes parallel. It becomes one resistance, and then the rest of the circuit becomes. Then we apply voltage over here. Then we have to nodal analysis over here to find the voltage. How much voltage, because this two becomes parallel, but these two are not in series because this resistance over here. Now, if you neglect this resistance, this two will become after this parallel connection, and this will be in series. And then you can derive the rest of the circuit by finding. It's not that easy, but I have written down the overall equations. So for the input resistance, step by step, you find that one, and you find input, and you find the input and then output, and then the voltage all the way. So, but really, to find the RO is what I just described before. We need to short the input and eventually to apply voltage over here but okay, one more thing I need to be careful is that usually when we look for output resistance, we don't include the load because the load is not part of the amplifier. So if you look at the whole amplifier, which is really just this, in the middle part is the amplifier. So therefore, when we look for output resistance, we usually don't consider this one. So we remove this one, and then we apply voltage over here. And then because voltage you apply, you can find how much current over here, and you can find the current over here, and the current over here, and then you can look for output current over there. And then you can also get rid of this one, but also you can include, in this case, actually, they're included. So, but once you included these two actually in parallel, because we short this one, so these two in parallel, and then that's why in parallel and divide by this one, and then plus RE. Okay, and in parallel with RE and all that, you get RO. So we got the output resistance. We are not going to ask you to derive how to calculate output resistance. So basically, I know it's kind of crazy because the process is very tedious. Right? It's not that easy. So, but what I want you to explain to you is you understand the process how to derive it, and then write down this equation. I don't expect you to even memorize it. I don't remember it, so it's okay to write it down so that you can reference later. And for using the same procedure, we can also find the input resistance and so on. So therefore, that will be a little bit easier once we go on to analyze the like generic amplifiers in the future. So let's take a break. I know it's a lot of information, yeah, to digest. Let's take a 10 minutes break and then we'll come back at 4:50. Yeah.
How much of them can you like, oh, like let's say it's emitter follower or whatever, like you can just do that and just use the formula that we already have versus, oh, we need to derive anything. Because of course they may have, oh, extra resistors or
Yeah.
extra branches.
I would
So I
say,
feel like you have to do all the
yeah.
steps anyways, right?
The important thing is that to understand what type of amplifier you have. Once you know what amplifier is, and you can directly plug in like the equations. But
So
if
they don't change.
they don't change. But if you get it wrong, you say, okay, if it's coming emitter, but you think it's coming collector, it will be totally wrong. So no matter what you do, you will not get the right result.
Yeah, so what I'm saying is like, for example, like in the textbook, there's like a bunch of, like, there's just huge tables like, oh, like this is equal to that, et cetera.
Yeah.
But that's only for like the simplest version. So how would you, let's say, augment, let's say if it has extra branches or it's more complicated than just like the simplest version?
The first step will be to simplify that to the model that you want to use.
Oh, okay, so let's say a bunch of resistance, you just make it into an equivalent.
Yeah, just make it equivalent. Yeah, right.
And then you use it.
Right. Like let's say
Yeah,
you
it's
have,
not so much easier.
yeah,
Trying to do everything step by step.
right.
Okay.
So once you get down to that, okay, now I got the circuit. Yeah, it's the same. I can
Yeah.
now do the equations.
Yeah, it sounds so much easier. Just doing it every single time, step by step, it's so much.
Oh yeah. No, it's impossible. Yeah.
Okay, thank you.
This is gonna be chapter 7.
Yeah.
Yeah, for you. But if he had you
Okay, so let's get started. I know what I have talked looks like easy to speak, but actually to do it is hard. So, but actually, if you really follow the procedures and you understand the principle behind the logic behind it, it's not that difficult. But of course, again, as I said, I don't expect you guys to like memorize how to do this, but it's really good to understand the logic so that if you ever had a need, you will be able to say, okay, well, I know how to do it. I know the process. It's just tedious, but I can still do it, right? So in this example, for example, if you want to find the input resistance, now, as I said before, you want to find the input resistance, what you need to do is you need to, well, in this example, what they did is they're trying to include everything. So even include the load resistance, which sometimes I don't agree because the load resistance is not part of the circuit, but you can include it for the simplicity. Now, in this case, see the way that they did it is first of all to look at RIB, is to look at the resistance between the input node of the BJT or the MOSFET and then everything rest. But the circuit over here is really because if you look at the gain here, RO is connected from here to ground. That's important, right? So ideally, you can simply remove this one and connect to ground. You see, because it's ground, right? G is the C is ground. So move that to ground, it doesn't change anything. So now you see you have these three resistance in parallel. So you will be able to really just use this one, just forget about everything else, just simply do one like resistance to ground. So this is going to be like something called IL prime, right? So now you got rid of this one, so this whole circuit becomes this. And this RL prime. Okay, so now you see what happens? These two in series. So immediately you got this total resistance with this one, RE plus RL prime. Now, but the next step is that we need to convert the whole thing over here into a resistance. Now the problem is the control source. If you don't have a control source, it's easy, it's just this. Since you have a control source, the total resistance from this point on to this side has to be calculated by applying like a voltage here, like you apply Vx here, and then you would find out how much Ix, and then this resistance they call RIB is equal to Vx over Ix. But the Vx is easy, is what I assume that Ix, of course, is going to be this current. This current minus this current, right? So this current is going to be Ix is going to be, so this is alpha times I. So this is alpha times I, and this current over here is I. So you have alpha times I comes in. Actually, you have I times R coming in. You have Ix coming in. Let's do it this way. Equal to I. So you have I equal to Ix divided by 1 minus alpha. Okay, so you'll find like this. So now you have Ix equal to, and then your I equal to Vx over Re plus RL prime. So that's resistance over here. So now you have I, and then okay, so you either this equation or this equation you can find Ix. Once we find Ix, we plug in here, we cancel the Vx, we get IIB.
So that's what we got from the top equation over here. That's how we got it. Okay. Now, if you got that one, this whole equation now becomes, the whole circuit becomes so you have now, really, the whole thing here is RIB. Now you have these two in parallel, right? That's what we have here in parallel. Now you can do the voltage divider now. So input over here is we are in divided by this one, and you have VO, and you have the gain. So everything follows very straightforward. So that's how you do this just step by step. And for RO, it's very similar. Basically, again, you would like short this one, and these two become in parallel. And once these two in parallel, you move this one again to the ground. So this is important, is because this thing here really bothers me and bothers you too. So you move this one RO to the bottom. Okay. So now you have all this 1, 2, 3 in parallel, and this 3 in parallel, and then is with series with this one. Okay. And then similarly, now you can do you can apply voltage over here and to see and make a short circuit over here. This two becomes parallel, and you can calculate the nodal analysis over here by using this equation, and you use this voltage here divided by the current going through here. Eventually, this is what you get. So we don't have time to go to really to the very much details, but let's move on to our chapter 8. So chapter 8 basically talks about the basic building blocks of integrated circuit, because the reason that we learn this is to build amplifiers. And we can use BJT and MOSFET to build a single stage amplifier, but often you will find that a single stage either has too much input resistance or too little input resistance or too much output resistance, or the gain not enough. So what we do, we have to connect multi-stages. And another reason is we want to eliminate the resistance, because building a resistance inside IC is very difficult. So therefore, we have to construct some sort of basic building blocks to how to form like the fundamental component for an integrated circuit. The first component we learn is a current source. So instead of using resistance to bias BJT or MOSFET, we use a current source. And the current source is not existing naturally in life. So we have voltage source. You can buy a battery. A battery is a voltage source. But there's no such thing that you can go buy a current source. It just doesn't exist. So we have to build a current source using a voltage source. So we can develop a power supply. We can develop a voltage, a current source, a voltage source, and then from voltage source we get a current source. So maybe you guys also understand that for voltage source we can have an open circuit. They can have a battery. You leave it there, it's okay. Nothing happens. You cannot short a voltage source. If you short it, what happens? If we short a voltage source, what happens? Sparks, bias. So if we have a voltage source, we short it, what happens? There's a little bit of resistance inside. So basically you have a current which is voltage divided by a very small, like internal resistance, and it's approaching infinity. Basically, if you try it at home, see what happens. You short your battery, it's not going to kill you. Your battery will become very hot, very quickly because a lot of current flowing. And in the beginning, if you short it, it have a spark because too much current. So your battery will die within like a couple, like maybe a minute or so, it will die. You cannot short a battery a voltage source. Now, if you have a current source, what happens? Did you guys learn? What do you do with the current source? Can you have it open? Why? If it's a current source, means current has to flow. It cannot be stopped. If you stop, it will generate a very high voltage, very high voltage, very high voltage, just like the current very high, very high. So and this thing will not work. So you're gonna have trouble. So basically, for a current source, we have to short it. You short a current source, it's okay, and its current just keep flowing, and nothing would happen. Now, I mean, in real life, you have resistance, and it will consume some power, but the ideal source is okay. So to build a current source, we can use either PJT or MOSFET. We'll look at both. The way to build a current source is to have two MOSFETs or two BJTs back to back. And then back to back means they're going to share their gate. They're going to share their gate. If they share their gate, what is the gate to source voltage for those two transistors? Are they going to be the same? Not zero. They're going to share because this is not ground. So from gate to source, they share the gate, they share the source. So therefore, you will have, let's use capital now because this is for DC biasing. So we will have VGS1 equal to VGS2 because they share the gate, they share the source. So VGS1 is the same as VGS2. That's number one. Number two, the drain of the reference transistor, which this one, usually on the right hand, it's left hand is a reference. The reference transistor's drain and gate is connected. Now, sometimes you might put a resistance here. It's okay. You don't have it. You don't need to have it. But because there's no current, so you put a resistance, it doesn't happen. It doesn't change anything. So we just do this direct connection. So drain. So two D1 is connected to remember, if drain is connected to gate, what operation mode is this transistor going to be? Triode? Saturation, right? It's going to be in saturation because your VGS minus VT minus VTN is going to be always less than VDS, which is same as VGS. So VDS is same as VGS, it's always large, so there's in saturation. Because D and gate are connected, so VDS is always same as VGS, and always larger than VGS minus VTN, so it's in saturation. And the third point is that once you are in saturation, we know in saturation, we can easily calculate the current of ID1. Okay, do you remember? You guys remember the equation for ID? And VOV squared, yeah, okay. So that's your ID1. it's interesting to see that ID1 has nothing to do with R. Is that right? I mean, yeah. If the circuit is given, if we know what VGS is, it has an. However, VGS has something to do with R1, with R in this case. Why? Because we really don't know what VGS is at this point, right? But once you know ID1, can you calculate VGS? What is the VGS? So VGS really just here. I mean, VG because S is the ground, so VGS same as VD, same as VDS, same as VGS. Okay, so how do you calculate it? It's VDD minus ID1 times ID1. So we get VG. Okay, so we have VGS now calculated. So we, well, of course we have not calculated, but we need to plug in VGS here to get ID1 on this side, ID1 on this side. So now we can actually find what ID1 is eventually. Yeah. Oh, this, yeah. Thank you. Yeah. What I'm saying is not what I'm writing. It's interesting. Yeah, yes, right. Okay. So now so we need to plug in this equation to here. We get a second order equation for ID1, and we can find ID1. Okay, so we find ID1. Now the next step will be, now we find ID1. How do we find ID2? Okay, so in order to distinguish this one, we will use W2 over L2. Because VGS is going to be the same. And if K is the same, and in fact, K is always the same, because they're made on the same wafer, so they have the same semiconductor properties. So K is always the same, but they can make it W different. So W2 over L2 can be the same, or it doesn't have to be. But if it's the same, apparently, what would you find? So if W over L1 equal to W over L2, and then ID1, ID2 equals same as ID1. So that's the important conclusion, is that if they have the same channel width, channel length, then the current of the second transistor is identical as the first transistor. Because it's identical, so we call this a current mirror. So what we are saying is Q2 is mirroring the current in Q1. It's a current mirror. But if, okay, you might say, okay, what happens if they are not the same? Well, if they're not the same, then ID2 will be ID1 times W over L2 over WL1, which means ID2 is going to be proportional to ID1, and the rate is based on the ratio between the channel width and channel length. So which means if the second transistor is much bigger, in terms of W, it's much bigger, then the current will be bigger. So sometimes in the future, we will say, how many X? So we got 2X, 4X, add X. What does it mean? That is the second transistor width over channel length, channel width over channel length is 2 times, 4 times, or 5 times, or 8 times the first one. So the current in the second one is much bigger. And we call that, it's like a current steering circuit. Now it's not mirror anymore, because mirror has to be the same. Okay? If it's not the same, it's not a mirror, but it's steering. So, okay. So in current mirrors, we normally neglect early effect VA just because it's not going to impact the current mirroring. In the future, once we get to the point, you will see that if you consider VA, There's going to be a slight difference between the second one and the current, but the difference is going to be something like 0.1%. So it's negligible. So therefore, we're going to neglect VA when we calculate the current. Now, instead of call it ID1 and ID2, in the future, we're going to call this I reference and IO. Okay, so IO is a current source, and I reference is a reference current. Now, in fact, instead of using a resistance here to get what the current you need, we can get a current reference current. Well, we can build the reference current in a different ways in the future, but think about it. We replace the resistance with a current source. So now we have a purely current mirror, no resistance at all. No resistance, just transistors. And our output, this current source, IO, and it's going to be the same as reference, or IO can be I reference times if these two don't have the same channel width and length, you're going to see a different current. And we use this a lot in the future because this one doesn't give you any resistance, so it's really nice to have. And then we're going to move on. Once you have like a current source, you can start to make multiples instead of just one, because I can make a multiple. Like in this case, remember what we did is initial example is between these two, right? So now I'm going to add a Q3. What is the current in Q3? Can you tell me? Well, if they have the same channel width and length, what happened to this current? It's going to be the same because you see, they share the gate, they share the ground, which means VGS is the same. VGS is the same, which means they will have the same current. So this I3 and I2 are going to be the same. Now, of course, if the channel width is not the same, you can easily calculate how much I3 is going to be. Okay, now I'm going to connect this one here. You see, how much is the current in transistor Q4? Well, they're connecting in series. So Q4, I4, I3 are going to be the same. Now, look at Q5. What happened to Q5? Q5 gate is connected to Q4 gate. And over the gate is connected to drain. Is this a PMOS? Okay, now this is PMOS. Look at this is PMOS, not NMOS. So therefore, I5 is going to be the same as I4 because these two share the same gate to like a source voltage. Okay, I'm sorry, the source here, the drain's up there. So I5 is going to be the same as I4. You can keep add this, and in a transistor, like have 1 million transistors in it, probably half of them, maybe 1/3, are actually used to build all kinds of current source and current mirrors. And the current can be the same, or it can be double, triple, quadruple, whatever that you need. Simply use them to build, and you can to different. You can build 100 of them with the same reference, with only one single resistor. So some of the chips only have one single resistor. You will have all of that. So this is called current steering because you're steering one to another, to another, to another, and you can have multiple. Okay, nowadays you say, okay, well, you have a current source. You can't have an open circuit over here. Remember I said before, you cannot have an open circuit. If this current I2 flow in, it flows to ground, it has to come from somewhere. So what happens to here and what happens to here? Well, that's exactly where the amplifier comes from. Because all we have right now are the current steering or current reference or current source that we're generating. Now you need to put an amplifier. Therefore, you will have amplifier with a current source that you need for the biasing. So for example, we can put an amplifier over here, or we can put an amplifier over here as well. Now, if we put an amplifier over here, we have a current source at the bottom, which means this are going to become something like a, let's do one so you guys see what it is. Let's say we do this. Let's do this. And we'll simply just have this RD and have V1 here, and we have VGS, which is in this case V into VGS. So what type of amplifier do you have? Well, it's not certain yet because we have input at the gate, right? And then we have output at the drain. So this is a typical common source amplifier. Now, of course, because it's current source over here, so this is not exactly grounded because it's current source. Now, I want to ask you, well, the current source is DC. For small signal, DC is open circuit. So which means we're going to open this. If we open this, our source is not actually grounded. It's going to be open, right? So the whole thing is not going to work. So what would you do then? If you were to design the amplifier, what would you do? You cannot have the source open because it's not going to work. We can put a capacitor. We can put a capacitor. So which means for DC, there's current source, you do the biasing. For AC, we're going to have this short circuit. So everything here becomes short circuit for AC. So your whole circuit becomes amplified, right? So this is a truly common source amplifier, right? Now for here, I can put this at the, so this one, I can do the same thing. I can do maybe two examples. So one example will be, okay, so now I put amplifier over here, and I ground the source, and I take my input output over here. What type of amplifier do you have? This source is grounded. This is common source amplifier. It's very typical common source amplifier. But then you have something at the drain, and this one at the drain is the equivalent, like if we don't have a load here, that's going to be something like an equivalent resistance. Later on, we're going to find out. But if you have a load resistance over here, it will be easy to draw the equivalent circuit. So the whole circuit over here will become because this current source over here, that whole thing is equivalent current source is gone in DC. It's an open circuit. So all the way I5 is open. Therefore, only one resistance can connect to output. So this is very basic gain unit. We're gonna again, we're gonna take a look at this also later on. So you guys are gonna see like again and again all these different amplifiers, the basic gain unit, the common source, common gate, common drain, common this, common that. Because all the way we do this and then we do this way, just to make sure that at every stage, like you, this enhance your understanding. Okay, so when we build a current source, sometimes it's important to understand that if the current source is coming from a voltage source, we call it current source, which means it's providing current. It's providing current. But if the current source is going to a negative voltage source, we call this a current sink, which means The negative current is attracting current. It's getting the current going in. So you can look at if this current coming VDD and this current here, this basically when we go to chapter 12, we're going to look at the classes of amplifiers. We're going to look at efficiency, things like that. You understand that this is providing power to the circuit, right? Because positive voltage times positive current and power comes in. So it's providing power to your amplifier for the DC biasing. But if the current sink, you see, your current is positive, but your voltage is negative. What happens to the power? You're assigning power to the voltage source. So that's why it's called a sink. Sink means attract. Okay, deposit like a sink current. So this is called current sink. This is called current source. This is just a terminology. Not a lot of problems with that. Now, you can do current mirror with MOSFET, but you can do current mirror with BJT. The only problem is that not exactly zero current. So therefore, if you look at it, okay, so we look at VBE is the same. So VBE is the same for both circuit. Remember when we calculate IC, do you remember how do we calculate IC in a BJT? IS times over VT, right? So now VBE is the same for both because their bases are connected. So VBE is same. So VBE Y equal to VBE 2. So therefore, IC1 and IC2 are going to be the same, correct? And from IC, how do we calculate IB? Okay, so which means this IB1, IB2. And over here, how much current is the one that I just draw here? What is the current over here? How much? The current going this way, the current going this way. So it's IB1 plus IB2, right? So it's IB1 plus IB2. And how much is I reference? Going to be IC1 plus IB1 plus IB2. So if IS1 equal to IS2, and then IC1 equal to IC2, and then IC1 equal to I reference minus like 2 times IB1. And IB1, remember, IB1 is very small because beta is typically about 100. So IB is about 1% of IC1. So therefore, what you're looking at, IC1 is only 2% less than I reference. So therefore, sometimes we try to neglect it. We think, okay, just assume IC1 is same as I reference, which, okay, if you are told to do that, you can do that. And it's not going to make a big difference. Okay, so this is a further analysis to the one that I just analyzed, the same thing, which basically tells you what exactly we do. So if we neglect, let me see what I do. If we neglect if we assume infinity, then IC1 equal to IC2 equal to I reference. Now I reference equal to VCC minus VBE over R, okay? And then from that equation,
previous equation, you know that VB IC actually equal to the IS times that thing, so you can, let me write down. So IC equal to IS times e to the power of VB over VT, right? So from this equation over here, you can calculate the current that you need. And then if the area is not the same, which means IS1 is not equal to IS2, and then they will be proportional. So current IO in this case will be proportional to I reference by like a ratio. It's area, surface area of 2 times surface area of 1. Because transistors, they are typically built based on the bin junction area. The larger the junction, the more current. So if they have the same area, you get same current. But if the second one is larger than the first one, you get more current. So BJT current mirrors are very much similar to the MOSFET, except that, yeah, the bed is not really infinity. But most of the times we can assume bed is infinity to simplify our circuit analysis. For BJTs, we can do the similar thing as what we did for the MOSFET. We can do a lot of them put together. So in this case, you look, Q2 and Q4, they form a current mirror because their bases are connected and then their emitter is the same. So therefore, they share the same VBE. Therefore, the two currents are the same. So you have the current here. Now then, you see Q7, Q8, and Q9, what happened? They're in parallel. And their base is all connected to the same base as Q2, which means these three are going to conduct the same current if they have the same area. So which means how much current do you have I4? If they're all the same identical transistors, how much current would you have in I4? It's 3 times I2, yeah, or 3 times I reference, right? 3 times. Okay, now we see at the top. You see at the top, we have this P-type, PNP type of BJTs, but if we have Q3 base, base connected the same as base at Q1. So therefore, can we imagine how much current in I1 if they are again identical? Same as IRF. And how much current would you have in I3? Twice I reference, right? So you can see that you can build like almost a lot of them. However, there's only one thing we have to be careful, is that because if you have too many, let's say we have 100, what happens? Because each base is going to connect 100 of this like reference current. So 1%, 1%, 1%. If we have 100 of them connected, it's going to be 100% of this reference. So therefore, you're not going to have the same current reference in this one anymore because there's too much current drawing into the base. So therefore, for BJTs, we have to be careful how many we can connect. You know, how many we can do from one. You just cannot do too many because there's base current. Yeah. How do you calculate? Well, the area is designed in the process for building the BJT. It's given. Yeah. So when you build a BJT, you can build that small, you can build that big. So the area is given, right? So that's current sources. And then here, okay. This example, we want to use to okay, we're still we want to do like the DC biasing calculations. I mean, this one is similar to the previous one that displayed, but slightly different. So in this example, we're going to assume beta is infinity to start with.
later on, if we want to do better, not infinity, we can do that. But let's start with assuming beta is infinity. And we want to look at how much voltage at each node and how much current at each branch for DC, again, biasing current. Also, we assume it's all in linear mode and the base to emitter voltage drop is 0.7. Where do we start? Q1? Why Q1? Oh, yeah, sorry. Well, you can start anyone, but you will find difficulty because you always have something unknown. Like for example, if we want to start here, okay, what calculate voltage? We need to find 5 volts minus voltage drop will get this voltage, but we don't know the current. Therefore, you got stuck, right? So we have to go back somewhere. So the only one that we can immediately get the current is Q1. Well, the reason is you see the top, which is in this case from the emitter to base is 0.7. So that voltage can be find out. So if that voltage is find out 0.7, and then we can in this case the collector is connected to the base, right? So we can find out .7 volts. So we can find, let's call this V1. Can you guys find V1 quickly? Q11, yeah. Where's Q1? Oh, okay. Okay. Yeah, so this is Q11. So let's call it V11 then. So V11 is going to be 10 minus 0.7 equal to 9.3 volts. Yeah. So we say, okay, this is the 9.3. And then we want to calculate the current, but the problem is that we don't know what you here. So again, okay, we got stuck again. So we really, okay, so I look at the wrong Q, so Q1 is actually here. The reason that we can find Q1 is, again, 17.5 volts minus 0.7, we'll find the voltage over here. So let's go to V1. So now, actually, we're going to find the V1. So V1 is 10 minus 0.7, 9.3 volts, right? 5, okay. You guys are really smart. Five minus. Oh, that one actually is 0. Sorry. So it's 4.3 volts. That one is 10. So that one is correct. So V1, we found V1. And then we will find V1. Okay. So we find V1, which is this voltage over here. And then we need to find, we want to find the current of I1. We need to find V1 minus V3 over R3. So the next step is that, so what I wrote is here. So if we find V1, because the same V1 here, if we can find V3, we can find the current over here. Now, how do we find V3? Well, because this is connected to the base, and base, see here, 0.7. So that's easy to find V3 equal to minus 5 plus 0.7. So we get minus 4.3 volts. So this is minus 4.3, and this is positive 4.3. The difference is 8.6 divided by 10. Now we got I1. So we find I1. So once you find I1, now we see, okay, so this I1 And then how much current is inside here? They're all identical. So this is twice the current. Therefore, how much voltage is here? This is ground. So this has to be lower than ground. So it's basically 0 minus the voltage drop over here gives you voltage over here. So you can find this voltage. And then let's go over here. So over here, you will find this current is the same as this current. And this current is the same as this current. So you can find voltage over here is this is ground. So current multiplied by 5 gives you current over here. Voltage over here. So we find that. And for this one, it's the same current. Basically, there's nothing to find because now we have the current and this 0.7 volts. Okay, nothing fancy. And then we come to here. So this is the current we know. Now we know this current is the same as this current. So now we know like a 0 plus voltage drop on here. We got this current over here. So it's very straightforward once you find current I1. So we're not going to go too much details on this one because I mean, you guys already found that. So I want to go back to the generic amplifier that I discussed a little bit earlier. So we enhance your understanding. So you have generic amplifier, AV, and your output here. AV is the voltage gain. And then you would have said that your in ideal case, idea is VO. Your VO is same as V in. In a non-ideal case, okay, non-ideal case you have. So this is the equivalent circuit. In ideal case, this is the equivalent circuit. But in ideal case, you have resistance. What happened? So, non-ideal case, you have RO, RE. In non-ideal case, we know that VO is going to be 2 voltage dividers. So this is an ideal case. You have two now with a current mirror like this, we try to understand what kind of impact you would have on the generic amplifier. Now, on the generic amplifier that we had on the last slide, is that we have this ideal case and ideal case. For the current mirrors, it's interesting that you repeatedly see, like sometimes it said, okay, ideal, sometimes it said non-ideal. So one of the questions that, do I consider this ideal or do I consider this non-ideal? Well, it depends on the situation. So you will be given, if you do a problem, you'll be given the instructions. So if it says you can do the ideal, you do the ideal. If it says it's not ideal, you have to consider the non-ideal. So in the ideal case, the current source is a current source. But in non-ideal case, any voltage source is going to have, like we just said, or any voltage source, it's going to have a small, sometimes not that small, resistance. It's called internal resistance. Like any battery, any voltage source is typical. So if you have your battery to supply power to your device, your device receives certain power, there's always a little bit of current, power loss inside the battery. That's why if the current is too big, your battery gets hot. Why it gets hot? Because there's resistance inside, there's power loss. So this happens to a voltage source. So you imagine that you have a current source. You would have some sort of resistance as well. How would you put the resistance with the current source? In parallel. So for any current source, you always have some sort of resistance in parallel. This is by just intuition saying, yes, I understand it got something, it has to have something. But in a principle, how do you get that? How exactly, how do I know how much this current is, right? All this resistance is going to be for any of the current source that we just derived from all previous current mirrors, current sources, multiples, one, a number of them. So how do you calculate? How do you calculate the current? Well, so this is what we're going to do. We're going to derive it. So let me actually let me do this. Let me erase this sentence just so you already understand it, so that I can now derive. So for we're going to look at this part of the circuit, and in particular, we're going to look at the equivalent, like the equivalent circuit. I don't know if you remember, in our very first lecture, we started talking about the large signal model, the DC model, equivalent circuit, and then we went on to talk about the small signal equivalent circuit. For MOSFET, because for DC, so now we're going to talk about DC. So for DC, we know that the DC current is going to be K times so this is kind of this is the current. And if we further look at how the current is related to VGS, is you can see that let me see what how do I explain this? It's going to be so I'm going to draw the equivalent circuit like I1, and I'm going to draw this Q1 and Q2. I'm going to draw the equivalent circuit. So S. So this equivalent circuit is going to become this is their gate, and this is a source, and this is a GM times so this is the idea. It doesn't look that nice actually, but this is the idea equivalent circuit. We have two MOSFETs. We have one MOSFET into here, MOSFET here. They share the gate, and then they share the source. So this is GM times VGS, and VGS is from here to here. And of course that, okay, we have to connect this one to here. So the gate is connected to the drain. So this is connected actually, but this side is not connected. This, in the ideal situation, we have this. But remember, when we derive, we have early voltage, we'll have this, actually, the early resistance is going to be connected. And this one too. And here, this current was this way. So this current I1 comes in, and the current I1 on the secondary. And then you can see here, immediately we have R01, R02, R02 introduced with the early resistance. So that's really where in the future we're going to say, if this is a current source, the equivalent circuit is going to have some sort of R02 and R01. So therefore, in the future, you're going to see also some sort of drawing like this. Just represent, in addition to the current source, actually you have a resistance, which is part of the transistor inside. I'm gonna go through a little bit more like detailed derivation here next week. This is see, the way that I draw was not that nice, but here is the equivalent circuit we draw over here. So R1, R02, they are basically drawn over this way. So this is the equivalent circuit for the for our current mirrors, and in the future we really try to use this, because eventually this becomes a large signal for current source for amplify. This becomes open circuit. So that's where we are going to yeah. So this is how to calculate R1. I'm going to start from this slide next week, and then we're going to continue, hopefully finish chapter 8 next week. Okay, so let's go to our quiz. Let's take a few minutes break. If you guys need to use the restroom and anything, feel free to do that. I'm going to make this, I'm going to set it up. So